When we're looking at the normal distribution, we explains some of the basic characteristics of normal distribution. And considering all these points, we did say that the points to note, some of the very important points, is that the normal distribution is the proper term for a probability bell-shaped curve. The normal distribution, the mean is 0, and in a standard normal distribution, actually, the mean is 0 and the standard deviation is 1. It has 0 skewness and a kurtosis of 3. Normal distributions are symmetrical, but not all symmetrical distributions are normal. Many naturally occurring phenomena tend to be close to the normal distribution. Now, when we talk about many naturally occurring phenomena, for example, let me give you I think we have a proper example here. For example, if you are to capture the heights, let's say you are to capture the height of female students, female SS3 students in Nigeria. Okay, you have to capture their heights. You will see that it will approximate the normal distribution. What does that mean? You will see that you will discover that most of the students will have heights that are close to the mean of the heights of all the students. So assuming the mean height of the student is 5 feet 2, okay, 5 feet 2. So what you will find is that most of the students will have heights close to them. Some will be a bit lower, some will be a bit higher. Okay. Now, when you go to the extremes, that's for those that are much taller than that, you find that the number of students will reduce. Okay. The number that are much taller will be low. That's what this curve that is coming down, that's what it means. So let's say, for example, students that will have height of 6 feet, they will be very, very few. Those are the extremely tall ones for that class. There's students that are much shorter than the average. Let's say like 4 feet 8. There will be very few as well. Or 4 feet 5. There will be very few. But around the center, which is around the mean, you have a lot more students. Okay, so that's what this shape is talking about. Now the extremely small values will be few. As you approach the average, you have more and more people. When you go past the average, the number of people also begin to drop. Okay, that's why we say that many naturally occurring phenomena appears to be normally distributed. This is a typical example of that. I hope that's clear. Hope that's clear. Take, for example, the distribution of the heights of human beings. The average height is found to be roughly 175 meters, 5 feet 9 inches, counting both males and females. In this case, this is a generalized case of both males and females. I use a streamlined one, for simplicity. As the chart below, this chart beside you can see here shows most people conform to that average, like I've already explained. Meanwhile, taller and shorter people exist but with decreasing frequency in the population. Okay? You yourself just look around as you walk around, you see that most people's are around average heights. Extremely tall people in society are few. And extremely short people in society are few. Okay. According to the empirical rule, 99.7% of all people fall within plus minus 3 standard deviations of the mean, or between 154 centimeters, that's 5 feet, and 196 centimeters. Okay. 99.7% of people fall within that range. So, when you begin to talk of people that are taller than 6'5", those are extremely few. Okay, like those basketballers. Those taller and shorter than these will be quite rare. Total of just about 0.15% of the population each. I hope we're on the same page.
Yes, getting it.
So these are important concepts in analytics, which we should know about. Okay, because as we move on and we begin to talk about some models, we hear that, for example, when we're dealing with ANOVA, and okay, sorry, I'm talking about that. Well, as we begin to deal with some models, you see some of them, you'll be told that the condition is that the distribution is assumed to be normal, that the distribution is assumed to conform with these characteristics of the normal distribution. Okay, so you should know what normal distribution is about, otherwise then it will be confusing, or begin to say such things. Okay, now let me say one or two things about this curve before we move on. If you look at this curve, you can see we have 175. If you look this way, say the average height is found to be roughly 175 cm.
Oh.
That 175 cm is the mean.
I just the rush in because I get the one online training.
That 175 is the mean. Okay. Then the median and the mode will also be about 175. Then I want you to observe something here. Now, when this normal distribution is drawn, is either you put these values, 175, how did you arrive at this 182? This tells us that the standard deviation, the mean is 175. The standard deviation is this gap you are seeing, this gap. The gap between 0 and 1, or between 1 and 2, or between 2 and 3. These gaps are standard deviation gap. So that's why we say standard deviation is a measure of deviation or departure from mean. So like here, from 0 to 1 here, what do you think is the value? That's 182 minus 175. What does that give? 182 minus 175 is what?
7.
Thank you. So now I want you to also observe 189 minus 182 is what? The same 7, right?
7.
Yes. And then 196 minus 189 is what? 7. Okay. So this gap, what I'm trying to say, what I'm saying is that this gap is the standard deviation. Let's go back. You can now see why here this is called mu, that's mean. This is called 1 standard deviation. This symbol is standard deviation. 2 standard deviation, 3 standard deviation. That's what that means. You understand? Then on the left, as you go toward the left, the values reduce here. From here to here is 1 standard deviation, but you will not say minus because you are now getting something lower than mean. That's why we say minus 1 standard deviation, minus 2 standard deviation, minus 3 standard deviation. Okay. Okay, and these values are used to compute the z-scores. That's why the z-scores for these values, these points will be 0, 1, 2, 3, minus 1, minus 2, minus 3. Okay. Now, when you draw a standard, when you draw a normal distribution and use these numbers, I mean, this smaller number, this 0, 1, 2, 3, minus 1, okay, instead of the actual, these are the absolute values, 175, 182. If instead of these, you choose to use these values, which are the z-score values, then we say that what you have is a standard normal distribution, not just a normal distribution, but a standard normal distribution. Okay, it's a standard normal distribution. So this is an example. This is a standard normal distribution. Although here we are saying we are adding the standard deviation here, but you could, instead of saying 1 standard deviation, you could just say 1. You could just call it 1, 2, 3, like that. So yeah, that's how standard normal distribution should actually be. Okay, so let's proceed now. Now let's move on to what we call data transformation. I've indirectly just mentioned a type of data transformation now. What I was explaining here is actually the z-score transformation. Okay. That's actually the z-score transformation. Okay. So you can see here, what has happened here is the mean value of 175 has been transformed to z, and the value became 0. 182, when converted to z-score, you get 1. When you convert 189 to z-score, you get 2. When you convert 196 to z-score, you get 3. Convert 161 to z-score, you get minus 2. How is that done? The formula is simple. It's say the formula here. Z is equals x minus mean divided by standard deviation. Okay. X minus mean, like if we go back to that table, remember our x, those are those big numbers. For example, when x is 175, and we know that the mean is 175, right? So x minus mean will be 175 minus 175 divided by standard deviation, which we got to be 7. 0 divided by 7 is what? 0. That's how this
0.
Yeah, that's how this 0 came about. Do you understand? Now, let's use this, for example. Let's use this 182, for example. 182. Let's go back to our, let's go back to, let me take you back to z scores. Remember, we said z is equals, this x in this case is 182 minus mean. Mean is what?
0.
No, I mean the big mean, the big figure for mean. 175, right?
Okay, for the, okay.
Yeah. So
175.
182 minus 175 gives what? 7.
7.
Divided by standard deviation, which is what?
7.
7. 7
7.
divided by 7 is what? 1.
0. 0.
1.
Okay, 7 divided by 7.
Yeah.
Okay. 1. Yes.
It's 1. That's how this 182 was converted and became 1.
Okay.
Okay. So that's an example of data transformation. But what's the purpose? What's the general purpose of data transformation? Now, why do you have to do data transformation? Let me go back and use that to illustrate why. Now, you can see that these bigger values, these big values, 175, 182, 189, 190 something, 150 something, they have been reduced to very small values of 0, 1, 2, -1, minus that. Okay, so when you do data transformation, what results is usually smaller. Usually you arrive at smaller numbers, which are usually more feasible for data analysis or computation that has to do with data analysis. So the data is easier to analyze because analysis is meant to be quick with the result coming up quickly and efficiently. So the purpose of data transformation is to streamline data, to streamline it, okay? To streamline data so that the values become small and the entire range of values also appears to be small, thereby making for efficiency in analysis. Okay, so that's the purpose of transformation. And now when transforming data, you use different methods, ranking, min-max scores, decimally scale scores, z-scores. Those are the popular things you do when you are transforming. Ranking. In statistics, ranking is the data transformation in which numerical or ordinal values are placed by their rank when the data are sorted. For example, the numerical data 3.4, 5.1, 2.6, 7.3 are observed. The ranks of these data items will be 2, 2, 3, 1, and 4, respectively. Do we agree with this? If I ask you to rank these values, how would you rank them? What would you do? If I ask you to rank this data, what would you do?
3.4. Because of our arrange them.
First of all, arrange them, right? You first arrange them.
Yeah.
So definitely, you know that if I ask you to rank that data, just like Charles said, the first thing you want to do is sort them.
Yeah.
Arrange them. Okay. So can you see my screen? Can you see my Excel screen?
Yes.
Okay.
Yeah.
So we have this data is not coming out as so we have 3.4. The second item was 5.1. The third item 2.6.
So your Excel screen is kind of probably, I don't know if it's
Small.
are you moving something? Because all we're saying is save, don't save, cancel. I don't know if you are still there or something.
No. That's not what you are supposed to be seeing. Let me show you. Is that what you are still seeing?
Okay, yeah, it's better now.
Okay. And then what's left now? And then we have a 7.3. Okay, these are our data. Okay, these are the data. This data, right? So we
Yes.
said to sort this, rather to rank these values. What do? You said the first thing is to sort, right?
Yeah.
Data, sort, and then we'll rank them. This should be the first. This is value. Let's call it X. This is the rank of the X, right?
Yeah.
The spelling is wrong. This is the rank. So this will rank as number 1, number 2, number 3, number 4, isn't it?
Yes, sir.
Okay. So that's ranking, but since we are doing analytics, you want to take advantage of the power of Excel to do your ranking, not just this manual ranking, right? But the important thing for now is that in ranking, what you do is, first of all, you sort the items, and then you assign values. You assign position to the data items. That's ranking. And that's considered a form of data transformation. Okay. Let me go back to that Excel so that I show you why it is considered data transformation. Well, so you see these values, no matter how large they are, just let's assume they were bigger values. Let's say this one were to be 26,000. Let's say this one was to be 34,000. This one were to be 51,000. And these were to be 73,000. These will still have been the ranks, right? Isn't it? Would the ranks have?
Yes.
This will still have been the ranks. So we can see the streamlining of the data. See the streamlining of this data. So you can see these data are now represented by these values. Okay, these big items are now represented by much smaller items. Okay, so that is that. That's the idea behind the ranking. I mean, when we talk of streamlining, once again, let's look at this. What is the range of this data? What's the range of this data? You know what I mean by range in statistics? What's the range of this data? The range of this data is equals what? Max of what?
Minimum.
Max
Minus minimum. Which
Maximum
is 3 minus minimum.
Minimum of these same numbers. Okay. So the range here is 47,000. What's the range here?
47,000. Okay, the range here is
maximum of this minus
3.
minimum of the same values. Okay, so when I talk about streamlining, you can now see what I mean. Here we have this value pass through. This is the range of values here. After computing the ranks, the range becomes 3. Can imagine the difference. So carrying out computation with these small numbers, carrying out analysis with these small numbers will be much faster, easier, more efficient than using these diverse numbers. Okay. All right. So now let's go back to continue. Let's go back to our slides. So that is the ranking. Is the simplest form of transformation. We also have the min-max transformation. That's another type of transformation. Meanwhile, we can also call transformation, we can also call it normalization. Okay, min-max normalization or min-max transformation. The min-max normalization is one of the most common ways to normalize data. Now, min-max is very commonly used. Min-max and z-scores are commonly used. Okay. In particular, I think min-max is very, very common in data science. Okay. Now, how does the min-max work? For every feature, the minimum value of that feature, what do I mean by feature? I mean, for every column, like let's say you have Excel data, each column of data is called a feature. Okay. So for every feature, every column, we could also call it for every field, the minimum value of that feature gets transformed into 0. The maximum value gets transformed into 1. And every other value gets transformed into a decimal between 0 and 1. So that's what happens when you do a min-max transformation. And this is the formula. You can see the formula there for min-max transformation. New value of x is equals x minus x min divided by x max minus x min. So that is how you do the min-max transformation. Okay. So let's see if we can, let's take a look at that. Just a minute. What screen are you seeing, please? What are you seeing on your screen?
the X and the rank.
All right. So if you look at this, these are data. Now, I want you to take note that despite we are using the scores now, the data could be very large figures, maybe some millions of, millions upon millions. No matter how large the figures are, when you do a min-max transformation, okay, all those values will then range from 0 to 1. You see the smallest number becomes 0, and the largest number, in this case now, the largest is 97, becomes 1. Okay, that's how the min-max transformation works. Is it clear? Let me copy out this so we can use it. So we can play around with it.